So today we have a seminar from Charlotte Goetz from Northumbria University, and they're going to be talking about the magnetic field of a comet. So thank you very much for giving the seminar today, and there'll be time for questions and discussion at the end. So whenever you're ready, thank you.
Yeah, thanks for the invitation, and thanks for bearing with me for the next 40 minutes or so. Yes, I will talk about the magnetic field of a comet, and we can jump right in, I guess. What will I talk about? So I'll first introduce comets. I will then talk a little bit about the Rosetta dataset, which is where most of our knowledge in the last couple of years came from. I will then introduce what the plasma of comets actually is, where it comes from, what it does. And because it's a really big field, I will not go into all the details of everything. I will focus on one specific thing, the diamagnetic cavity, and why it is weird. And then at the end, I'll just give a very small outlook on what we can expect from the future. So just on this slide, you can already see just change to a laser pointer there. So this picture I really love. It's a remote observation of a comet, but what I really like about it is that most people, when they think about comets, they think about what they can see in the sky, and usually that's just the white dust tail. But because this is plasma, we'll be talking about the blue bit, which is the plasma tail, which I think is much more interesting because there's more going on. So fundamentally, comets come from somewhere in the outer solar system. You have a little picture here of the solar system with its Kuiper belt, and then even the Oort clouds around it. And comets can come from anywhere in that region. You usually find those with small inclinations come from the Kuiper belt, and those with high inclinations usually come from the Oort cloud. So what are comets? So when I talk about the comet, I usually talk about the nucleus, which is a little bit in the middle. They're made up of dust and ice, and they're usually really small. So I think the biggest one that's detected as of yet is about 80 kilometers in diameter, but usually they're only a couple of kilometers. 67P, which is the one I'll be talking about the most, is about 4 kilometers. What makes them interesting, the nucleus, to people that are researching more dusty things and solar system formation, is that because they're from these outer bits of the solar system, they haven't really been changed since they formed, because they don't heat up because they're very far away. They're too small to experience any gravitational collapse. So we can, by looking at comets, we can kind of infer what conditions were at the beginning of the solar system. But for the sake of this talk, we're not going to focus on that. We're going to focus on the properties below, which is that they're not magnetized, which again helps with models for solar system formation. But to us, that just means that we don't have to deal with any magnetic fields that are produced by the comets. And really importantly, they're outgassing as they approach the sun, simply because there's ices that, as they get heated, they start to sublimate. And you can see this very nicely in these two pictures. So this is Comet Halley. This is an image that Giotto took, and you can very, very nicely see the dust and the gases coming off of it. The pictures I put here, there's a bit of a trick, because this is not actually technically a comet, the one in the bottom right. It's a trans-Neptunian object. It's the Kuiper belt object that was visited by New Horizons. But you can very clearly see that compared to the other comets that I've pictured here, it looks very similar, and that's because they're basically the same thing. It's just that the comets that we visit and that we're interested in, the one that outgas, they are basically Kuiper belt objects that have been put on an orbit that brings them close to the sun and heats them up. Right. Oops, sorry. I will introduce you a little bit to the Rosetta dataset. So Rosetta was launched in 2004. It was the European Space Agency mission to Comet 67P, Churyumov-Gerasimenko. And it took 10 years to actually get there. So it arrived in 2014 and orbited the comet for over 2 years. It has many, many instruments, because if you send something to a comet and you spend a billion euros, you want all of the instruments on it that you can get. So it has many cameras and dust detectors, but it also has a plasma suite. This is called RPC, Rosetta Plasma Consortium, because it's made up of different instruments. And so you can see here this IES, which is an ion and electron sensor. We also have ICA, which is the composition analyzer. So this can not only measure the energy of the ions, but also the mass. And then we have MIF and LUP, who can measure frequencies and densities and temperatures of the plasma. And then we have LUP again on this side on the boob, and we also have the magnetometer, which I'll be using quite a lot in this talk. As you can see, this boom is not fantastically long, which means that it's not easy to calibrate the measurements that we have. So we always need to treat them with a little bit of, let's say, suspicion if they do something weird. So what are the pros of this whole thing? Well, we do have measurements. They're the best measurements we have at Comets. All of the other ones were from flybys, which only lasted a couple of hours, while this was over 2 years. And we do cover the entire evolution of the comet. The negatives here are that we only have 1 point measurement, so we can only measure where the spacecraft is. It's very hard to calibrate because it's not optimized for plasma. It's optimized for all of the instruments on it, and cameras, for example, like to be 3-axis stabilized, so we can't spin the spacecraft very much for calibration. And we also have a very negative spacecraft potential, which makes it difficult to measure the electrons and ions at low energies. Anyway, we got what we got. So what did Rosetta do for 2 years? It basically hung out at the comet. So this is the entire mission lifetime from August 2014 when it arrived at the comet. You can see it coming in here. So the blue line is the radial distance of the spacecraft from the comet. And then we end here in October, or end of September 2016. And at the same time, you can see in red the heliocentric distance of the comet and the spacecraft. So you can see that we arrived at roughly 3.6 AU, and then followed the comet to its perihelion around 1.24 AU in August 2015, and then went out again until the spacecraft was deliberately crashed into the comet in 2016. So one problem with this is that the comet environment is not the easiest to navigate. The gravitational potential is not super even just because of the shape. But at the same time, you want to get quite close. And so this was done, especially at the beginning, where we had to do some mapping to deliver the lander to the surface, which was done here in November 2014. And you can kind of see the spacecraft going away afterwards again. Then there was a request for some close flybys to get as close to the surface as possible and to get some radial coverage as well. So you can see the first close flyby here in end of February 2015, which went well. It was really good. They then tried that again end of March 2015, and it triggered a safe mode in the spacecraft because Rosetta navigates by sight. And you can see in this really, really lovely video, all of these white dots here, they're dust grains that come off the surface. And while you can also see the stars in the background, some of these dust grains in the navigation camera can look like stars, and it can confuse the spacecraft quite a lot. And so there was a decision made by those in charge to fly as close as possible without endangering the spacecraft. So in essence, what this means is that all of the distance from the comet, basically during the time around perihelion, it's very much dictated by how much dust is coming off the comet. So if there's more dust coming off, it means the spacecraft will go further away. But the dust and the gas are correlated. So the more gas comes off, the further away the spacecraft will get. And that makes it really difficult to distinguish all of the plasma effects, because we're basically hanging around roughly in the same region as it expands or contracts, because we always expand or contract the trajectory with it. I'm not going to say more about this because there's lots going on, and later on in the talk we'll only focus on kind of this region in the middle. Anyway, yes, so if you like this topic, then I suggest you read this paper that we published last year. It's a very long review, but a lot of work went into it, and I think it turned out really well. So if you at some point have questions that I don't answer in this talk, do take a look at the paper. So I've been talking about the gas production rate already. So again, at the bottom, you will see this line quite a lot. It's the heliocentric distance of the comet. And at the top, we have the gas production rate. So this is the amount of molecules that come off of the comet per second. And characterizing this is not easy because it changes quite quickly. But there was an effort made by Casey Hansen at the University of Michigan to model the gas production rate and to kind of provide a best estimate, but quite smooth model with a Monte Carlo code that kind of traces back the actual measurements to infer a global gas production rate. This is very useful if you want to look at long-term trends. However, if you're interested in more local and more shorter time scales, we found that actually taking the measurements of the neutral gas density by the spacecraft and inferring a gas production rate from that is a better estimate of the gas production rate, as it is important for the plasma. So that's the red line, and you can see that it varies quite a lot. Very clearly have a peak around perihelion, so perihelion is here. And then the gas production rate goes up to 10 to the 29 at the most. As the comet is far away from the sun, we have very low gas production rates. But here at the end, for example, you can see that the DSMC model underpredicts the gas production rate a bit. And this is simply because the spacecraft was much closer to the comet in these last couple of months. You can also see lovely periodicities, which is the spacecraft trajectory, and all of these spikes here, that's the rotation rate. So the comet has two active regions, which means that every half rotation rate, about every 6 hours, you have more gas produced. And just to put this into context with all of the other comets that were visited by spacecraft, you have the gas production rate here at the bottom and the closest approach distance of the spacecraft. You can see Rosetta covered quite a lot, but it also covered a previously unknown region. Only Giotto at Rick Skeller covered a little bit of this. All the other ones were at significantly higher gas production rates or significantly further away. So this mission's really filling a gap here. Right, so how do we get from the gas that comes off of the comet, from the neutrals, to the plasma? Well, we need ionization, right? So there's a really nice paper by Simon-Wieland, which came out in 2019, where it's a set of 3 papers. They're really lovely. And at the end, basically what comes out is a really good model for the different ionization modes at the comet. So in this figure, you can see again the entire mission lifetime, and then you can see the different ionization channels. So the gray line is the photoionization, and you can see that that very much dominates during the perihelion time. But we can also see that electron impact ionization in pink here can dominate quite a lot at low gas production rates. And the problem with this is that it's really hard to incorporate in models because it depends on the electron temperature. And so it's really difficult to put this into like global scale models. Some people usually leave it out. There's also contributions from solar wind charge exchange and impact ionization, but that is very much lower than the other two channels. But basically, roughly what we can say, and we've already seen in the gas production rate, is the closer you are to perihelion, to the sun, the more gas and plasma is produced. The other driving force at the comet that kind of determines the shape of the plasma environment is the solar wind. So unfortunately, there's no upstream monitor for Rosetta, so we have to resort to models and kind of guessing. And this figure kind of gives you an overview of what roughly the solar wind parameters will look like. It won't be, you shouldn't like believe in this too much, but sometimes it's very good to have. But basically we see, as expected, the magnetic field increases as you get closer to the sun. The Parker angle decreases. And then obviously the density also increases closer to the sun. And while the average of the solar wind velocity is quite constant, on short time scales, it is very variable. So this is one of the problems that we have to deal with, is that we don't really know what the solar wind velocity or the magnetic field or the density is at any given moment. And that makes it quite difficult to interpret the data. Right. So what actually happens at the comet? Well, so on the left-hand side here, we have the nucleus that spits out the gas that then gets ionized. And the gas that comes out of it is mostly H2O+. And it comes out at very low velocities of about 1 kilometer per second, sometimes even lower. And that's kind of the cometary plasma. On the other side, we obviously have the solar wind at a speed of roughly 400 kilometers per second, mostly made up of protons. So these are much lighter ions, but it also has a magnetic field. And so we have these two plasmas that interact with each other. One is very slow and heavy, and the other one is very light but fast. And this is fundamentally what determines this interaction region, because somehow these heavy ions need to be picked up. It's in a process called mass loading and incorporated into the solar wind flow to make the tail, the lovely plasma tail that I showed at the beginning. And the process of how this works differ based on the activity, so based on how many ions there are. So this is a figure from our review paper, and it basically gives you an overview of the plasma environment at the comet at different activity stages. So low activity stage is here. I don't want to get too much into it because I won't be talking about it in the rest of the talk. But basically, all we have is some deflection of the solar wind and some acceleration of the cometary ions. But there's waves in the field, but there's no real regions that form. Everything's pretty uniform. And there's no bow shock or other boundaries yet. If we go to medium activity, weird things start to happen. This is just because when we describe the plasma environment, we always jump between the fluid description of the plasma and the hybrid description, or even the fully kinetic one. And especially the cometary ions have very large gyro radii. And this can induce really weird structures where, for example, the magnetic field is kind of dragged around the comet in a direction that's very counterintuitive. I'm going to show that later a little bit. But for the rest of the talk, we'll be dealing with the high activity here. So I'll focus on that a little bit more. So, as I said, there's so much going on can't talk about everything. So I will talk about a study that was published this year, about solar wind protons that are found in the diamagnetic cavity. So the reason why I want to talk about this is that I found the diamagnetic cavity super interesting. It's the only region in the solar system that's completely field-free. So if you look at this sketch of the environment, you have the sun on the right-hand side and the nucleus of the comet in the middle, and spitting out all of its plasma, and it somehow manages to keep out all of the magnetic field from the solar wind, and you find this really lovely field-free region. And we don't really understand how this works properly. We don't know where the boundary is, why it's wavy, and so on. So it's always fun to look at new measurements or interesting measurements in this. Right, so what do we expect to measure? So if you imagine your spacecraft sitting on these 3 dots, there's 3 different regions. So at this point in time, down up here, what you excuse me. So what you see is that the solar wind comes in from the right-hand side, and it gets decelerated because it has to transfer some energy and momentum to the cometary ions. It's usually done through the convective electric field, but I'll come back to that later. And at some point, a bow shock or bow wave forms, but the solar wind ions are still present in the flow. They're slowly being substituted by cometary ions, but they're still present and observable. So at this point here in the region, in the outer region of the interaction of the environment, you can still see the solar wind, and the magnetic field from the solar wind is also still present. However, we then come to this interface that we call the solar wind ion cavity boundary, which is this broad pink line here. And what it is it's the boundary of the solar wind ion cavity, right? So if you look behind it, there won't be any ions from the solar wind. If you look in front of it, there will be ions from the solar wind. And the reason this forms is simply that the solar wind is deflected around this inner interaction region, and it cannot penetrate this bit. So if you were to measure anywhere here, you would measure no solar wind ions anymore. Instead, you measure the pickup cometary ions that are produced upstream, accelerated, and then take over the role of the solar wind ions in the flow. And you can still see the magnetic field, which is starting to be draped around the inner interaction region. Then we move even further inside into the diamagnetic cavity, where the magnetic field is 0 because it's being pushed out. And we still don't observe any solar wind ions because they all flow around this inner region. And that's roughly what we expect to see. Before I get deeper into that, I just wanted to show you some nice measurements to convince you that this deflection of the solar wind actually exists. So this is again the spacecraft trajectory and the comet's trajectory in the solar system. And then the upper panel shows you the deflection of the protons as measured by ICA. And you can see that at low gas production rates, they're pretty much clustered around 0-degree deflection, which means they're just straight up from the sun. It's undisturbed or less disturbed solar wind. But as you increase the gas production rate, so as you go closer to perihelion, you can see that the deflection of the protons increases and increases and increases. And this is simply because of the momentum exchange with the cometary ions. So the solar wind starts to kind of dive down under the comet. And this deflection gets so extreme that as you go really close to the sun, you have very high gas production rates. You expel all of the solar wind ions, and this is the solar wind ion cavity. And in fact, Rosetta was located in the solar wind ion cavity for months during perihelion because you never went out far enough to leave it. And then based on this, we can also talk a little bit about the field draping. So if we look at the low activity case where we have almost no deflection, very low activity, what we observe is that the magnetic field of the comet mostly is in the direction of the Parker angle, as we would expect for an undisturbed solar wind. However, as we go closer to the sun at high activity, we do not see the cone angle of the magnetic field on this Parker angle line anymore. Instead, it's very much moved upwards. And this is the draping that we would expect. So that both of those things actually exist, which is nice, because not all our theories are wrong. Right, but that was kind of an excursion just to convince you that this nice picture that I showed you here is kind of correct. And now we go to the case where it's not correct anymore. So what does this look like? So I've talked about the diamagnetic cavity before. In measurements, this is what it looks like. So if you look at the bottom here, that's the magnetic field measured by the spacecraft. And you can see that there's loads going on, and in the coma, there's like super fun waves and all kinds of stuff. The fields at this point piled up and draped already. So it's at 20 nanotesla, where the solar wind field should be more around 3 nanotesla. But you can also see that suddenly Rosetta is entering this region where the field is extremely quiet, and it's also very close to zero. Rosetta leaves this region again and then enters it again. Just remember that the spacecraft is moving very slowly. It's 1 meter per second. So what this actually means is that this diamagnetic cavity is expanding and contracting because it needs to kind of move over the spacecraft. And so this is what I call the normal case for the purpose of this talk. Because what we see is that if we move up here to the second panel, panel B, there's no real detections of solar wind ions, which this is, right? This is the solar wind ion spectra as measured by ICA. You can see that there's a couple here, but they're so insignificant that we can disregard them. And then if we go to the bottom, we can see that the cometary ions are, well, basically very low energy, which is in agreement with our theory that the cometary ions that are produced inside the cavity are at low energies and then very slowly get accelerated. While outside of the cavity, the cometary ions can be quite fast already. However, we find upon closer examination that in 5 instances, there are actually solar wind protons in the diamagnetic cavity. So you can see down here again the magnetic field, very clearly diamagnetic cavity measurements. We can see very clearly the lower energy cometary ions. And then when we go and look at the solar wind ions, we also see very clear signatures. And this is super weird because they shouldn't be there. They should have been deflected around the entire region. I mean, very far upstream, we should not be able to see that. And then at the top here, these are the moments, so the actual velocity moments of the solar wind ions, and you can see that they're quite fast, actually. So they are at 350 kilometers per second, which indicates that they're not really slowed down at all. And we can also see that the X component down here is the most significant one, the largest component, which indicates that they're anti-sunward. So they come from the sun. And so this very much looks like non-deflected, non-decelerated protons that we see here. And that's really weird. We would not expect that. So the rest of this talk will kind of try and explain why this is happening. Right, so let's first of all try and figure out when and where these 5 events are found, where we have protons in the diamagnetic cavity. So in brown here, you can see the dwell time of the spacecraft in a coordinate system that's made up of the gas production rate and the cometer-centric distance of the spacecraft. You can see that most of the time is spent down here. This is simply because at the end of the mission, at the beginning of the mission, the spacecraft spent a lot of time very close to the comet. But at higher gas production rates, it's all pretty pretty well distributed. The blue points then show you when the spacecraft was able to measure the cavity, and you can also see that this is very well distributed. However, all of the events where we observe protons in the cavity only occur close to the comet and at low gas flux rate. So just before we cease to be able to measure the diamagnetic cavity, these things turn up, which means that we find them only there. We don't find them at high gas production rates. So this is the first clue that we need. Because that basically means that the diamagnetic cavity already is quite small and quite unstable. And that makes it easier to measure these weird things. Then we can look at which direction the protons come from, and I've already alluded to this. So these are the events. And you can see that anytime the protons are inside the cavity, we see them preferentially at very high x speeds, and we also see them preferentially at lower radial speeds, which indicates that they're not inflected and they come straight from the sun. So what does this mean? Well, basically, to be able to explain these observations, we need a situation where the solar wind is not deflected for some reason. But at the same time, we also need the diamagnetic cavity to expand, because if it wouldn't expand, the spacecraft would not be able to measure it, because it's just sitting at the same point all of the time. And there's a bunch of things that can cause this. We can go through all of them. So the first one would be a neutral gas or dust outburst. So basically, sometimes the comet goes a bit crazy and spits out all the gas, but there's no enhanced neutral density during any of these events, so we can rule that out. There could also be a CIR or ICME impact. We've observed those at comets before, and they do lead to an extension of the diamagnetic cavity, and they do influence the solar wind velocity. However, when we look at model predictions of the solar wind velocity here in orange, so our 5 events are 1 here, 3 here, and 1 here, we do see that the velocity seems a bit elevated towards these 2 events, but there's nothing going on here. And even at these 2 events, it's not particularly high. And in our data, we also do not see the impact of a CIR, which is usually associated with increased electron temperatures. So we can also rule out this one. So the next one I like because it's a bit sneaky. So basically what we can also do for the protons is we use charge exchange, right? So we have the proton coming in from the sun, and it charge exchanges and becomes neutral. And then it doesn't feel any of the influence of the plasma clouds anymore. So there's no deflection because it doesn't feel the electric field, and it doesn't see that there is a comet actually. So if we charge exchange this solar wind proton far enough upstream, it can basically dive under the whole plasma interaction region, and we then make it into a ion again closer to the comet, again through charge exchange, and suddenly we have a proton that's been basically undisturbed since it was charge exchanged the first time. And so my student Lucy, she put this into a model with the help of Cyril, and basically we look at 2 reactions, so proton H plus H2O plus, which then makes the H, and then we go back again to H plus, and we can calculate the flux ratio, but we find that the flux that of these kinds of protons is very low, and it is not sufficient to explain our observations. I should point out that at Mars, this does happen. There is charge exchanged protons that can occur in the ionosphere, but the ionosphere there is much denser, and there's much more going on in terms of charge exchange than at the comet. So yeah, that also doesn't work. And that leaves us with our last bit, which is that the solar wind magnetic field could be parallel to the solar wind velocity. So what does that mean? So I've talked about pickup and deceleration and deflection, but the way this works is basically that the cometary ions, they sit there and they feel the convective electric field of the solar wind. And so they get accelerated by this convective electric field into the direction of the convective electric field. So the cometary ions moving in this case upwards. In turn, to conserve momentum, the solar wind has to be deflected downwards. And this is the deflection that I've been talking about. And this is very nice. We see this in observations and simulations. It's super lovely, works great. The problem is, it doesn't work anymore if you put the solar wind magnetic field parallel to the solar wind velocity, because there's no convective electric field. So the cross product ends up to be 0. And suddenly you end up with cometary ions that are not accelerated and also protons that are not deflected. And this is exactly the situation that we're looking for to explain our results, because we want the protons to not be deflected. And so basically what this means is that the more parallel the velocity and the magnetic field get, the more inefficient the energy and momentum transfer between the cometary ions and the solar wind ions, because the only pathway of transfer that's still open is through wave-particle interactions. And those usually take quite a long time, while the interaction region is still quite small. And there were some really lovely simulation by Christoph Kunders already in 2013, where he varied the angle between those two vectors in the solar wind. And he found that the standoff distance of the bow shell decreased with angle, which is an indication of the efficiency of the energy transfer. So this is nice because it actually seems to work. So that leaves the condition B, the one where we want the diamagnetic cavity to expand. So we don't really understand yet how the diamagnetic cavity is formed and what the pressure balance is at the boundary. However, what we do understand is that the magnetic field pressure that pushes at the boundary at the diamagnetic cavity plays into it. So the higher the pressure, the smaller the cavity. And so the higher the pressure means the higher the magnetic field. If we have this configuration here, we don't see pickup really. So we don't see pileup either. And there were some simulations by Tamas many, many years ago where he simulated this kind of conditions. And he actually found that as you go towards the inner coma, the magnetic field here in a solid line just decreases and then enters the diamagnetic cavity. And then in green, I've kind of put in the normal case, which is where the solar wind velocity and magnetic field are perpendicular, where we very clearly would see pileup because of the deceleration of the solar wind and the pileup of the field. But in this case, we can't pile up the field because that would violate the divergence free condition. And so what this ends up happening is that under normal conditions, we have pileup, and that's a very high magnetic field value just before the cavity and high pressure pushing the magnetic cavity inwards. While in the parallel case, there's no pileup, so very low magnetic pressure, and that allows the diamagnetic cavity to expand. And so that means that we can also satisfy condition B. I want to close with two things. So this is basically my attempt to summarize the two conditions. So on the left-hand side, we have the normal case. We have the solar wind deflected. I do apologize, it's now the other way around because no one can ever settle on which direction the sun should be at. But we have very nice deflection from this solar wind coming in from the left-hand side. We pick up the cometary ions in purple. They take over the flow, and it's all very lovely. The diamagnetic cavity expands and contracts, and so we can measure it. But there's no solar wind ions in the diamagnetic cavity. In the parallel field case, there's no deflection, so the solar wind can just go in, and we also do not see any acceleration of the cometary ions, except for a bit through wave-particle interaction. And I just want to point out that this is not the only body where you see this, because Mars is the same thing. So there's a study by Chris Fowler from last year, where again we have the normal case. Now the sun's on the other side again, sorry. But we have the normal case, lovely, lovely deflection and mass loading of the solar wind, and everything's nice and pretty. However, when you switch to the radial IMF case, suddenly there's no deflection of the solar wind in red, so it can just penetrate the inner ionosphere. And also you observe that all of the boundaries are degraded and the foreshock region is extended, simply because there's more wave activity going on. And so I really like this because we found something at the Comet, but at Mars and also at Venus, you can find very similar conditions, and it's nice that it actually all fits together. Right, that brings me to the conclusions. What do I want you to take away from this? Well, I think comets are super interesting plasma environment. They're very, very complicated because we have different kinds of ions, and the source of the disturbance is so small that it doesn't really matter. So all we're dealing with really is an ion cloud. It is similar to Mars, but there are differences. It is similar to Venus, but there are differences. So it's just a really lovely laboratory to study plasma and the interaction with things. The diamagnetic cavity is influenced by the solar wind strength and outgassing. We've known that for a while, but now we also know that it's influenced by the Parker angle, and quite radically as well. And then the last one conclusion is that the magnetic field in general is highly dynamic. It's really hard to describe it properly. And the draping that I showed actually only works at large timescales, and you really need to dive into the details to understand it. Right, last slide, the future. What are we doing now? So I want to say thanks to Herbert Grinnell and Charles Patemi for running simulations of this radial field conditions, and you can already see some preliminary results where the field is perpendicular to the velocity in the upper panel, and then lower panel is radial, and you can see that it just looks completely different. And it seems to agree quite well with our observations. So we'll have to write up the paper soon, but then that will hopefully also come out. And the other thing I wanted to point out is that Rosetta was not the last mission to the Comet. We have a new mission coming up. It's called Comet Interceptor. It will launch in 2029, and it's kind of the next step in cometary exploration. And it also has a bunch of plasma instruments, and most excitingly, it actually has 3 different spacecraft. And we were able to measure the magnetic field at 3 points instead of just 1 point, and thus we will be able to disentangle the temporal and spatial effects, which is not possible with the Rosetta dataset so far. So we're all really excited for this mission. And with that, I'll shut up and answer any questions you may have.